Welcome! In this session, we'll tackle an exciting coding problem titled Minimum Swaps to Make Strings Equal. We'll break it down step by step, explore different approaches, and analyze their efficiency. Let's dive in. Here, we are tasked with solving a problem involving two strings, S1 and S2, which are of the same length and only consist of the characters X and Y. The goal is to make the two strings equal using the minimum number of swaps. A swap involves exchanging one character in S1 with the character at the same index in S2. If it's not possible to make the strings equal, we return -1. For the input format, we are given two strings, S1 and S2, both strictly composed of X and Y. The output is an integer that represents the minimum number of swaps needed to equalize the strings, or -1 if it's impossible. Let's look at some examples to better understand the problem. In the first example, S1 is XX and S2 is YY. The output here is 1. This is because we can make the strings equal with a single swap. If we swap the first character of S1 with the first character of S2, S1 becomes YX and S2 becomes XY. Now, both strings are equal, showing that the minimum number of swaps required is 1. This demonstrates how swapping works to resolve mismatches at corresponding indices. In the second example, S1 is XY and S2 is YX. The output for this case is 2. To make the strings equal, we first swap the first character of S1 with the first character of S2. After the swap, S1 becomes YY and S2 becomes XX. Then, we swap the second character of S1 with the second character of S2. After the second swap, both S1 and S2 become XY. A total of 2 swaps were required to make the strings equal. This example shows how multiple swaps may be necessary to resolve mismatches in more complex cases. In the third example, S1 is XX and S2 is XY. The output here is -1 because it is impossible to make the strings equal. No matter how we attempt to swap, the mismatch at the second index cannot be resolved. Looking at the constraints, the lengths of S1 and S2 can go up to 10,000. Meaning we need an efficient algorithm to handle large inputs. Additionally, edge cases include scenarios where the strings are already equal, requiring 0 swaps, and cases where mismatches make it impossible to equalize the strings, leading to an output of -1. These examples and constraints help clarify the problem requirements and guide us in designing an effective solution. To solve this problem, we first need to consider a brute force approach. The brute force method involves examining all possible swaps between the characters of the two strings, S1 and S2, to minimize mismatches at each index. For example, if the characters at index I of the two strings are not equal, we attempt swaps to see if they bring the strings closer to alignment. However, this approach is highly inefficient. Each mismatch could require multiple swaps to resolve, and since we need to evaluate all possible swaps, the time complexity increases to O(n²). This makes the brute force method impractical for larger inputs, especially when n can go up to 10 to the power of 4. Additionally, brute force does not take advantage of the problem's unique structure, where only two characters X and Y are involved. Therefore, while the brute force approach might seem intuitive initially, it is not suitable for this problem due to its inefficiency. Instead, we use an optimized greedy approach that focuses directly on the mismatches between S1 and S2. The key insight here is that mismatches can be categorized into two types, XY, where S1 has X and S2 has Y, and YX, where S1 has Y and S2 has X. A critical observation is that the total number of mismatches must be even for the strings to be made equal. If the sum of XY and YX mismatches is odd, it's impossible to solve the problem, and we return -1. To resolve mismatches efficiently, two XY mismatches or two YX mismatches can be resolved with one swap each. However, resolving one XY and one YX mismatch requires 2 swaps. Using these rules, the process becomes straightforward: traverse the strings once to count the XY and YX mismatches, check if their sum is odd, and calculate the minimum swaps needed based on the mismatch counts. The algorithm is simple, with clear steps that ensure correctness and efficiency. The optimized greedy approach is efficient in terms of complexity. With a time complexity of O(n), we only need a single traversal of the strings to count mismatches, making it suitable for large inputs. Additionally, the space complexity is O(1), because we only use a few counters to track the mismatch types. This strategy is particularly effective because it directly leverages the specific structure of the problem, which involves only two characters, x and y. By focusing on the mismatches and resolving them in the minimum possible steps, the greedy approach avoids unnecessary computations and achieves optimal performance. A key trade-off is that this approach is tailored specifically for problems involving exactly two distinct characters. While it sacrifices generality, this trade-off is justified given the constraints of this problem. The simplicity and clarity of the approach make it both easy to implement and highly efficient. While alternatives such as bit manipulation or hashing could encode mismatches more compactly, they would introduce unnecessary complexity without improving runtime efficiency. These methods are less intuitive and do not align as well with the structure of this specific problem. The greedy approach, on the other hand, strikes an ideal balance between efficiency, clarity, and correctness. By directly addressing the mismatches and leveraging the problem's constraints, it provides a clean and effective solution. This combination of simplicity, efficiency, and focus on the problem's unique characteristics makes the greedy approach the best choice for solving the minimum swaps problem. To solve this problem, we need to determine the minimum number of swaps required to make two given strings, s1 and s2, equal. Both strings are of the same length, and a swap is defined as exchanging two characters at specific indices within a string. The process begins with input validation. First, we confirm that the lengths of s1 and s2 are equal. If they are not, it's immediately clear that making the strings equal is impossible, so we return an error or a special value, like -1. On the other hand, if the strings are already identical, no swaps are needed, and we can simply return 0. Next, we analyze mismatched characters by traversing both strings simultaneously. For each position where s1 and s2 differ, we record the mismatched characters and their indices as tuples in a list called mismatches. For instance, if s1 is ABCD and s2 is ABC, the mismatches occur at indices 2 and 3. These mismatches are stored as 2CD, 3DC, which lays the groundwork for resolving them efficiently in subsequent steps. The goal now is to resolve the mismatches with the minimum number of swaps, and we achieve this using a two-pass approach. In the first pass, we focus on direct pair resolution. Here, we look for mismatched pairs where the characters are inverted, meaning a swap between their indices will resolve both mismatches in a single step. For example, if we have the mismatched pairs 2CD and 3DC, swapping indices 2 and 3 in S1 directly fixes both mismatches. Each such direct resolution increments the swap count by 1, and these pairs are removed from the mismatches list. In the second pass, we handle any remaining mismatches through indirect resolution. For each unresolved mismatch, we search for the nearest index in S1 where the character can be swapped to resolve the mismatch. Each of these operations adds to the swap count as we iteratively address the mismatches. Once all mismatches are resolved, we return the total swap count as the result. Now, let's delve deeper into the key insights that make this algorithm efficient. First, direct pair resolution is crucial for minimizing the number of swaps. By resolving mismatched pairs where characters are inverted, such as 2CD and 3DC, we avoid unnecessary intermediate swaps and significantly reduce complexity. Second, for mismatches without direct resolution, the algorithm adopts a greedy approach, finding the nearest matching character to resolve the mismatch with minimal additional swaps. This strategy ensures that the swaps are performed efficiently. Finally, prioritizing direct resolutions before tackling indirect ones allows the algorithm to optimize for the lowest possible swap count, leveraging the natural structure of the mismatched pairs to achieve the goal in the most efficient manner. To implement this approach effectively, we rely on two key data structures. The first is the list of mismatches, which stores tuples containing the indices and characters involved in each mismatch. For example, the format of this list might look like index char underscore in underscore s1, char underscore in underscore s2. This structure makes it easy to track mismatches and process them iteratively during both the direct and indirect resolution phases. The second is a simple swap counter, which keeps track of the total number of swaps performed. This counter is incremented whenever a direct or indirect resolution is performed, and it provides the final output of the algorithm once all mismatches are resolved. Analyzing the complexity of this algorithm, we see that it is highly efficient. The time complexity starts with an O(n) traversal of the strings to identify mismatches. Resolving these mismatches involves iterating over the mismatched pairs, which takes O(k), where k is the number of mismatches. In the worst-case scenario, k can be as large as n, making the overall time complexity O(n plus k), which simplifies to O(n). In terms of space complexity, we need O(k) to store the mismatches in a list. Since k is proportional to n in the worst case, the overall space complexity is O(n). This efficiency ensures that the algorithm scales well even with large input strings. Finally, let's consider some important edge cases. If the strings are already equal, as in the example where S1 is ABC and S2 is ABC, the result is zero swaps since no mismatches exist. On the other hand, if mismatched characters cannot form valid swaps to resolve the differences, as in S1 being ABC and S2 being ABD, we return -1 to indicate that making the strings equal is impossible. Additionally, for large inputs, such as S1 being A repeated 10,000 times and S2 being B repeated 10,000 times, the algorithm ensures efficient handling by maintaining its O(n) time complexity. These considerations showcase the robustness of the solution across a wide range of scenarios. This code provides a solution to LeetCode problem number 1247, minimum swaps to make strings equal. The problem involves determining the minimum number of swaps required to make two strings equal, where each swap exchanges two characters at specific indices between the strings. The function minimum swap takes two input strings, S1 and S2, which are guaranteed to have equal length. The solution works as follows. 1. Mismatch counting asterisk. We iterate through both strings simultaneously using zip, S1, S2, to identify mismatched characters. Specifically, mismatches are classified into two types. XY_count counts occurrences where S1 has X and S2 has Y. YX_count counts occurrences where S1 has Y and S2 has X. 2. Odd mismatch check asterisk. If the total number of mismatches, XY_count plus YX_count, is odd, it is impossible to resolve all mismatches using swaps. In this case, we return -1. 3. Resolve mismatches asterisk. To resolve mismatches, each pair of XY and YX mismatches can be fixed in one swap. Thus, XY_count //2 and YX_count //2 swaps are used to address as many mismatches as possible in pairs. If there is one unmatched XY and one unmatched YX, i.e., XY_count %2 = 1, it takes exactly two additional swaps to fix them. 4. Return result asterisk. The total number of swaps is the sum of the above components. This approach is efficient, with a time complexity of O(n), where n is the length of the strings, as we only make a single pass through the strings. The space complexity is O(1), as we use a constant amount of extra space. Here, we begin with the implementation of the solution in Java. The method, minimum swap, takes two strings, S1 and S2, as input. The goal is to determine the minimum number of swaps needed to make the two strings equal. First, we initialize two variables, XYCount and YXCount, to 0. These will keep track of the mismatched character pairs, XY and YX, respectively. Next, we loop through the strings character by character using a for loop. At each index, we compare the characters from S1 and S2. If we encounter an X in S1 and a Y in S2, we increment XY count. Similarly, if there's a Y in S1 and an X in S2, we increment YX count. This allows us to count the total number of mismatched pairs. After the loop, we check if the sum of these mismatches is odd. If it is, it's impossible to balance the strings, so we return -1. This is because mismatches need to occur in even numbers to be resolved through swaps. Now, we focus on how we calculate the minimum swaps needed to resolve the mismatches. Each pair of XY or YX mismatches can be resolved in one swap. So, we divide XY count and YX count by 2 and add these results together. However, if there's an unmatched XY and YX left, meaning both counts have a remainder of 1, it will take 2 additional swaps to resolve them. This is handled by checking if XY count %2 is equal to 1. If that's the case, we add 2 to the result. Finally, we return the total count, which represents the minimum number of swaps required to make the strings equal. This approach ensures an efficient solution with a time complexity of O(n), where n is the length of the strings.
To solve this problem, we first need to analyze the mismatches between the two strings.
Starting with S1 as XX and S2 as YY, we initialize two counters, XY_count, which will track the mismatches where S1 has X and S2 has Y, and YX_count, which will track the reversed mismatch, where S1 has Y and S2 has X. Next, as we iterate through the strings, we compare each pair of characters. For the first pair, X in S1 and Y in S2, we increment XY_count by 1, making it 1. For the second pair, which is also X and Y, we increment XY_count again, resulting in a total of 2. At the end of this loop, we find that all mismatches fall into the XY category, so XY_count is 2 and YX_count remains 0. We then check if the total mismatches, which is the sum of XY_count and YX_count, is even. Here, the total is 2, so it is possible to make the strings equal. This check is crucial because if the total mismatches were odd, it would be impossible to resolve them through swaps. Now that we know it's possible to resolve the mismatches, we calculate the minimum number of swaps needed. Each mismatch pair, whether XY or YX, can be resolved in 2 swaps. For this example, with XY_count equal to 2, we can resolve one full pair using XY_count ///2, which gives us 1 swap. Since there are no remaining mismatches, XY_count %2 is 0, no additional adjustments are needed. This means the minimum number of swaps required to make the strings equal is 1. Let's now move on to another example where the mismatches are slightly different. For S1 as XY and S2 as YX, we will again follow the same process to compute the result. For S1 as XY and S2 as YX, we start by initializing XY_count and YX_count to 0. As we loop through the strings, the first pair of characters is X in S1 and Y in S2, which is an XY mismatch. This increments XY_count to 1. The second pair is Y in S1 and X in S2, which is a YX mismatch, so YX_count becomes 1. At the end of the loop, we have one mismatch of each type, XY_count equals 1 and YX_count equals 1. The total mismatches, XY_count plus YX_count, is 2, which is even, so it's possible to resolve these mismatches. To calculate the swaps, we note that a single XY mismatch and a single YX mismatch can be resolved together in exactly 2 swaps. Since there's only one mismatch of each type, the total number of swaps needed is 2. In this example, we consider S1 as XXYY and S2 as YIXX. As usual, we initialize XY_count and YX_count to 0. Then, we iterate through the strings to count the mismatches. The first pair is X in S1 and Y in S2, so we increment XY_count to 1. The second pair is also X in S1 and Y in S2, so XY_count becomes 2. The third pair is Y in S1 and X in S2, which increments YX_count to 1. The fourth pair is another Y in S1 and X in S2, so YX_count becomes 2. At the end of the loop, we have 2 mismatches of each type, XY_count equals 2 and YX_count equals 2. The total mismatches are 4, which is even, meaning it's possible to make the strings equal. With this setup, we can now calculate the minimum number of swaps. To resolve the mismatches in this example, we note that each full pair of mismatched XY and YX can be resolved in 2 swaps. Here, XY_count //2 gives us one full pair of XY mismatches that can be resolved with 1 swap. Similarly, YX_count //2 gives us one full pair of YX mismatches, requiring another swap. Since there are no remaining mismatches, XY_count %2 and YX_count %2 are both 0, no additional swaps are needed. Adding these together, the total number of swaps required to make the strings equal is 2. This approach ensures that we account for all mismatches efficiently while minimizing the number of swaps needed. To analyze the time complexity of the solution, let's start with the mismatch counting step. Here, we loop through the strings S1 and S2 using the zip function, which allows us to iterate over both strings simultaneously. Since the length of these strings is n, the loop runs n times. For each pair of characters, we perform constant time operations to check mismatch cases and update the counters XY_count and YX_count. This means the mismatch counting step has a time complexity of O(n).
Next, there's a simple arithmetic check to determine if the total number of mismatches is odd. Since this is a single arithmetic operation, it runs in constant time, or O1. Finally, the result is calculated using integer division and a conditional check, both of which are also O1. Combining these steps, the overall time complexity of the solution is dominated by the mismatch counting loop, making it O(n). Now, let's evaluate the space complexity. First, we need to consider the storage of the input strings S1 and S2. Since both strings have a length of n, they require O(n) space. Additionally, the algorithm uses a small, fixed number of auxiliary variables, such as xy_count, yx_count, a, and b, to track mismatches and intermediate results. These variables occupy constant space, or O1. Importantly, this solution does not use any additional data structures, such as lists or dictionaries, nor does it involve recursive calls that would add to the space complexity. As a result, the total space complexity is determined by the input size, which is O(n). Let's examine the best, average, and worst-case scenarios for the algorithm. In the best case, the strings S1 and S2 are already equal. Even then, the loop must iterate through all n characters to verify the equality, resulting in a time complexity of O(n). The space complexity remains O(n) due to the input size. In the average case, the algorithm needs to count mismatches for all characters in the strings, which still requires O(n) time, with space complexity unchanged at O(n). In the worst case, every character in S1 and S2 mismatches, meaning the algorithm processes all characters to compute the minimum swaps. Even in this scenario, the time and space complexities remain O(n). It's helpful to compare this optimized solution with a brute force approach. A brute force method might involve finding all the mismatch indices and then generating all possible combinations of swaps to check if the strings can be made equal. Identifying the mismatch indices would already take O(n) time. However, trying all possible swaps introduces a combinatorial explosion, as the number of swaps grows factorially with the number of mismatches. This results in a time complexity of O(n) in the worst case. The optimized solution avoids this inefficiency by directly counting mismatches and calculating the minimum swaps mathematically, reducing the time complexity to O(n). Finally, let's validate the big O complexities mathematically. The main loop iterates through n characters, performing constant time operations for each pair. This step gives us a time complexity of O(n). Subsequent calculations, including arithmetic checks and result calculations, are all constant time operations, contributing O(1). When these are combined, the overall time complexity remains O(n). For space complexity, the input strings dominate with O(n), while auxiliary variables add O(1). Since the input size dictates the space usage, the total space complexity is O(n). This confirms the efficiency of our solution. One common mistake when solving this problem is ignoring edge cases like empty strings or strings of unequal length. If one or both strings are empty, or their lengths differ, a solution is impossible, and the function should immediately return -1 or signal an error. For example, if S1 is an empty string and S2 is ABC, no alignment can be achieved. Another error is assuming characters are always swappable. If the character frequencies in S1 and S2 are different, no amount of swaps can make the strings equal. Take S1 as AB and S2 as AB, the mismatch in character counts makes alignment unattainable. Lastly, inefficient swap simulation can be a pitfall. Iterating unnecessarily over already aligned positions wastes computation time. Instead, focus on tracking which positions are mismatched and concentrate efforts there. Another mistake to watch out for is overcomplicating the logic. Using unnecessary data structures like nested dictionaries or multiple lists may seem helpful but often adds to the time and space complexity without solving the problem more effectively. A direct approach that maps characters between the strings is usually sufficient. Additionally, not validating the output after performing swaps can lead to subtle bugs. Once the swaps are complete, it's crucial to verify that the transformed strings are indeed identical. This step ensures the correctness of the solution and avoids overlooking small errors. From an interview perspective, this problem tests your ability to translate logical operations into efficient algorithms.
A key skill is recognizing patterns in string manipulation problems, whether it's using two-pointer techniques, frequency counting with hash maps, or another method. Optimization is another focus. Start by explaining a brute force approach, but quickly highlight its inefficiencies and suggest ways to refine it. This progression demonstrates your ability to improve and adapt. Proactively addressing edge cases like empty strings, unequal lengths, or unswappable characters is a great way to show thorough understanding. Finally, if there are multiple solutions, be prepared to discuss the trade-offs. For instance, a greedy approach might be faster but harder to implement compared to a more systematic dynamic programming solution. This problem ties closely to several related LeetCode problems. For instance, minimum swaps to make strings equal naturally connects to challenges like satisfiability of equality equations, where you need to evaluate relationships between elements. Similarly, 3 equal parts explores partitioning structures into equal segments, and minimum window substring involves finding the smallest substring that meets specific criteria. Each of these problems reinforces concepts like string manipulation, pattern recognition, and optimization, making them great practice alongside this challenge. There are several alternative approaches to solving this problem, each with its trade-offs. A greedy approach focuses on resolving mismatches in one pass, prioritizing swaps that immediately reduce the total mismatch. While this method offers faster runtime, often O(n), it can be harder to implement and debug. Another option is using a hash map to count character frequencies in both strings, ensuring they match before aligning mismatches. This method is easier to implement but may require additional space proportional to the size of the character set. Finally, the two-pointer technique is a straightforward approach where two pointers iterate over the strings, swapping mismatched characters directly. The logic here is simple, but it may fail for complex cases where multiple swaps are needed to resolve mismatches. Choosing the right approach depends on the problem constraints and your familiarity with these techniques. Great job! Today, we analyzed the minimum swaps to make strings equal problem, explored its solutions, and gained insights into optimizing string operations. Keep practicing, stay curious, and we'll see you next time. Don't forget to like, share, and subscribe. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!